All right, so this is chapter 6, and chapter 6 has all to do with how to name formulas and how to write formulas. Now, I just want to make a note that this lecture does not follow the book subchapters like 6.1, 6.2, that sort of thing in order super well. I kind of created my own set of material for this chapter, and so this is one chapter where it will not follow along as smoothly as the rest. So the first thing that we have to think about when we are figuring out naming and formula writing is what kind of compound we're dealing with. Are we dealing with a molecular compound, an ionic compound, or a hydrogen compound? So a molecular compound is going to contain only two nonmetals or could have a metalloid as well. And for this course, we're only talking about two nonmetals or a metalloid nonmetal sort of combination, but realizing that molecular compounds can have more than just two elements there. Ionic compounds are going to contain a metal in their formula or a polyatomic ion, and those are groups of nonmetals with a charge. And then we have hydrogen compounds, which are compounds starting with an H, and those could be a gas or an acid. So we're going to start off with the easiest, which is a molecular compound, and then we'll work our way through. So molecular compounds kind of have four different parts to it. So we've got the first prefix, which is going to tell us how many of the first element we have. We've got the first element. And so the first element is always written out to its full name. So you're never going to change the ending to that element. It's always going to be its first name. The second prefix is going to tell you how many of the second element we have. And then we also have the second element's name. But the second element's name, we're going to have to cut off the ending and add in an IDE. So this slide is really great at summarizing this all. Now, if we only have one of the first element, we aren't going to say anything in front of it. We're just going to say, like, for example, carbon monoxide. That tells us we have one carbon, and then monoxide is going to tell us we have one oxygen. All right, so you do need to memorize these prefixes. You do need to remember these kind of rules. So the first element is always going to be named the same way that its element is named. And that first element, if there only is one of that first element, you don't write anything in front of it. You just write the element's name. The second element is always going to get a prefix. It's going to get a mono through deca prefix. And then those are some examples of the second element names. So oxygen turns into oxide, nitrogen turns into nitride, and so on and so forth. So here are some different examples of names to formulas and formulas to names. So names to formulas, pentaphosphorus, that means we need 5 phosphorus, so P5. And then trioxide tells me we need 3 oxygen, so O3. The next one, carbon tetrachloride. Carbon has nothing in front of it. Because it has nothing in front of it and it's the first element, that tells us we need one of that. Tetrachloride tells me I need 4 chlorides. So 1 carbon and 4 chlorines. Pentasulfur dinitride, that's going to tell me I need 5 sulfurs and 2 nitrogens. And then here at the end, dinitrogen monoxide is going to tell me I need 2 nitrogens and only 1 oxygen. So I want you to practice going through these. Name the following compounds, so formula to name, and then also going from name into formula. All right, in this first one, we've got 3 phosphoruses and 5 nitrogens. So we've got triphosphorus, and then pentanitride. Make sure that you change that ending to IDE. Now the next one, we've got 2 nitrogens and 4 oxygens, so dinitrogen. And then we need tetroxide. Now, when we do this, if there's an A and an O, we typically drop that A and just leave the O. So instead of saying tetraoxide, we usually drop that A. Now, this next one, we just have 1 nitrogen. So we're just going to write nitrogen. Remember, you don't need mono nitrogen for the first element. You would if it was the second element, but the first element we don't need mono. And then we need dinitrogen. oxide. All right, and then to go from name to formula, we're just going to go through and figure out what elements we need and how many we need. So phosphorus, we know we need a P here. Since there's no prefix in front of it, that just tells me I have one. And then trichloride tells me I have 3 chlorines. So it's going to look something like that. Dinitrogen, N2, and then tetroxide. So we need 4 oxygens. And then this last one, dichlorine. So chlorine, I need 2. And then heptoxide, I need 7 oxygens. Now, please notice that in all of these, we have a nonmetal plus a nonmetal. That is the key to a molecular formula. Molecular formulas are more simple than the rest that we're going to talk about because it pretty much tells us how many we need. Or we go from the formula and can see how many we have to telling us how many we need in the name. So with these ones, we are not thinking about charges. Okay, the name or the formula tells us it all. So don't think about charges when we have a non-metal and a non-metal. All right, now we're going to get into ionic compounds. Now, ionic compounds get a little bit more complicated, and that's all because of the charges that we're involving. So we have a binary ionic compound, which just means that we're going to have a metal and we're going to have a nonmetal. So the metal is going to start our compound formula or name, and the nonmetal is going to end that formula's compound or name. Now, in ionic compounds, you never use the prefixes that we just learned. The prefixes that we just learned are only going to be used for those molecular compounds that we just talked about. We'll talk about one other instance where we need to use it, but it's not used within an ionic formula's name. Now, when we name binary ionic compounds, again, it's going to be a metal and then a nonmetal. So the metal is always going to get its normal name: calcium, magnesium, iron, potassium. Okay, always the normal name. And then the nonmetal is always going to end in that IDE ending that we just talked about. So chloride, bromide, iodide, oxide, that sort of thing. All right. So when we name metals in ionic compounds, there's 2 kinds of metals that we're talking about. There's one type of metal that always has the same exact charge no matter what compound it's in. And then there's the other metals that can change their charges based on what they're bonded with. So the rules to this: if a metal is in the first 2 columns of the periodic table, so like lithium, sodium, potassium, those that column there, or if it's in the next column, which is calcium, barium, strontium, rubidium, those ones there, those are always going to have the same charges. So first column is always +1. Second column is always a +2 charge. And then there's this nice little trick here. These are the other 3 that you have to have memorized that you do not need to think about charges. They're always going to be the same. And it makes this little stair step on the periodic table. So aluminum has a +3 charge, zinc has a +2 charge, and silver has a +1 charge. That is predictable. It looks like a nice little stair step when you look at your full periodic table. But those elements, those are the other 3 besides the first 2 columns that you always know the charge of. Now, why do we care about that? Why am I talking about this? Because the other elements, so our transition metals in the middle, and then the other elements that are over kind of below aluminum over in here, we've got things like lead and tin over here. Those other elements can change their charges, and when they change their charges, we have to actually tell us what it is. So if you are not in the first 2 columns and you are not silver, zinc, or aluminum, you're going to need a Roman numeral to tell us what charge you have. Okay. Now, these Roman numerals are going to go in parentheses right after the metal's name. And again, that Roman numeral is going to tell us what the positive charge on that metal is. So to figure out the Roman numerals, we need to figure out what charge we have based on the formula. So if we take a look here at what that kind of looks like, these are just the first examples, the non-Roman numeral examples. So first 2 columns, or aluminum, zinc, and silver. So right here we've got sodium and then iodide. Please notice that you just use the regular metal's name and then the non-metal's name gets an IDE ending. So sodium iodide, calcium chloride, aluminum oxide, zinc bromide, and silver fluoride. Please notice that those never have those prefixes that we just talked about. So it's not dialuminum trioxide. That's not how we name these. When you have an ionic compound, we just simply state the metal and the non-metal. Now, here are some Roman numeral examples that I was talking about. So for the Roman numerals for our metals, we are always going to know the charge of the anions, which are the negative charged ones, okay? And so what we need to do is we need to look at the charges of our negative anions, figure out how much negative charge we have. We have to have the same positive charge. So let's say we've got negative 8, for example, negative 8 charge. Then that means that our positive charge from the metal needs to be a positive 8. So we just have to do a little bit of math here to figure out what we've got going on. And so if we take a look here, we've got iron oxide. Now we got to figure out what kind of iron it is. Is it a +2? Is it a +3? So if we take a look, our oxygen O has a -2 charge. We've got 3 of those, so -2 times 3 gives us a -6 charge. Now, we have to balance that out with a +6. So the +6 needs to come from our irons. Now, we have 2 irons, so if we take 6 plus divided by 2, each iron is a +3. And so that +3 gets translated into this Roman numeral right here, I. Now let's review our Roman numerals here a little bit. Number 1 is just 1 I. Number 2 is 2 I's. Number 3 is 3 I's. Now it gets a little funky. If we want 4, we need an IV. If we want 5, we need a V. 6 would be VI. 7 would be VII, and we usually don't have to go past that. Okay, usually, quite honestly, we stop right around 5. We usually don't go above that. So let's take a look at a few more examples here. So if we take a look at this example, cobalt chloride, each chloride is a -1 charge. We have 2 of them, so a -2, and you only have 1 cobalt to use. So that cobalt has to be a +2 charge. So it's cobalt 2 chloride. You can see that Roman numeral 2 tells us that that metal cobalt is a +2 charge. This next one, we've got vanadium and nitrogen. So your nitrogen is a -3 charge. We only have 1 vanadium, so that vanadium has to be a +3 charge. So this is vanadium 3 nitride. Now, in the next one, we've got 1 phosphorus. That phosphorus is a -3 charge. And so we need a +3 charge. That +3 charge is going to come from the nickel. So +3 charge divided by 3 nickels gives us a +1 charge for each of the nickels. So that's where we get that Roman numeral 1, because each nickel is a +1 charge. The next one is kind of difficult. So each oxygen is a -2 charge. We have 5 of them, so we've got a -10. We need a +10. We've got 2 manganese to use, so +10 divided by 2 gives us a +5. That's where we're going to get that Roman numeral number 5. Now, this is sometimes how I write it out on my paper. I would have manganese oxide. I know that I have a -2 charge here. -2 times 5 gives me a 10 minus, so that means I need a 10 plus for my manganese. 10 plus divided by that 2 gives me a 5 plus, and that 5 plus is what I'm going to put in as a Roman numeral. Okay, so that's what I kind of do on my own paper. Now, let's take a second and name those following compounds. Some of them you're going to need Roman numerals, some of them you're not. Remember, you do not need Roman numerals if you're in the first 2 columns or if you're aluminum, zinc, or silver. All right, so going through these answers here, we've got our first one. This is potassium. Potassium is in the first column, so we don't need a Roman numeral, so we can just write potassium. And then we've got nitrogen, so that's going to change to nitride. This next one, tin, is not in the first two columns or in that staircase that we talked about. So we need tin, but we need to figure out its charge. So tin chloride, each chloride is a -1, so we get a -3 charge. That means our tin, since we only have one, has to be a +3. So it's tin 3 chloride. Now our next one, we've got zinc. Zinc is part of those three little staircase, so we don't need a Roman numeral. We can just write zinc. And then we've got oxide here. Now our next one, lithium is in the first column. Don't need a Roman numeral. We have lithium, and then that is sulfide. Now our next one, copper, is in the transition metal area, so we're going to have to figure that Roman numeral out. So we know we have copper. Let's figure out that Roman numeral, CuBr2. Each bromine is a -1 charge, so we have a -2 charge overall. Copper has to be a +2 charge, and there's only one of them, so the copper has to be a copper 2. And then we've got bromine, which turns into bromide when we name that. And then the last one here, we have chromium. And that chromium, we're going to figure that charge out here. Each oxygen has a -2 charge, meaning we have a -6 charge. The chromium has to be a +6 charge overall, but we have two of them. So 6 divided by 2 gives us a +3. So we've got chromium 3 oxide. All right, so those are just binary ionic compounds. And binary ionic compounds, remember, just have a metal and a nonmetal. Only two elements you're going to see in the formula. Now we have ionic compounds with polyatomic ions, and these are actually pretty common. So our polyatomic ions are a group of nonmetals that stay together and have a charge. These are the 7 that you must memorize, okay? You need to get these memorized. They are going to be on a reference doc, but they aren't going to have the names next to it, okay? So you'll have the formula and the charge. So you'll have, for example, like NH4 plus, you'll have that formula, but you will not know the name of it. So you have to start to get those memorized with each other. So ammonium is the only positively charged polyatomic ion that we have. Pretty much one of the only positive ones we have overall, not even just the ones you have to memorize, but this is our only positive. These next 3 are the -1 charges. So we've got acetate, nitrate, and hydroxide. Now, we've talked about these a little bit in previous chapters where we called them groups. So we've got like a nitrate group. And so when we go to use these, we have to keep them as a group. These next 2 are our -2 charge, and this is our -3 charge. So you do have to get these memorized. Now, the little note at the bottom is more so for like when we get into acids, or if you ever see anything that's very close to these but slightly different. If a polyatomic ion ends in ite, it has one less O than the 8. So what does that mean? Well, nitrate is NO3 minus. Nitrite with an ITE ending is going to be NO2 minus. Okay? Sulfite would be SO3 2 minus. So you can see there that we've got that difference of 1 oxygen. Now, again, that's mostly for when you get to acids. We're typically just going to deal with these 7 compounds when I give you examples, but I just wanted to point that out. So make sure you start getting these memorized. Again, on your reference doc, you will get all of this or all of that, but you will not get the name. So you need to start memorizing the name to the formula. And again, the charge is going to be there, which is pretty nice for you, but you will not get the name. So when we deal with these, we're really thinking about the charges that are involved. And so when these compounds are, when these ions are in our formulas, the names remain the exact same that you just saw on the previous slide. Okay. If we need more than one nitrate, for example, let's say we need 2 of them, you don't say dinitrate. We're just going to simply say nitrate. It's just like saying barium chloride. You have a barium and 2 chlorides. You don't say barium dichloride, you just say barium chloride. So these work just the same as any of our other ions that we have, except now it's a group. Their charges are always going to be known. So sulfate, for example, is always a -2 charge. The nitrate is always a -1 charge. Phosphate's a -3 charge. Those are always going to be known to us. Okay, and so we can use these charges to find the Roman numerals for the metals if we need to. So if we take a look at what that kind of looks like, this first slide here involves just the simple one, so without any Roman numerals in it. So we've got sodium, which is in the first column with a hydroxide, OH, so sodium hydroxide. We've got silver phosphate, so you're just stating the metal's name with the phosphate. We've got calcium nitrate. Ammonium chloride, this is kind of a unique one, again, because ammonium is the only positively charged polyatomic, so it's the only one that's going to show up first in the formula. Otherwise, the rest of those 6 are always going to be in the second part of the formula with a metal, but ammonium is always going to be in the first part and not in the second part. So we've got ammonium chloride, and then this last one would be zinc carbonate. So again, this slide here is showing you those different examples of the compounds that are in the first 2 or the metals that are in the first 2 columns, or in that kind of that stair-step line. And ammonium is kind of a unique one here as well. Now, when we deal with Roman numerals with polyatomics, it doesn't really change from what we just talked about. Now we're looking at a group of atoms rather than just like chloride is a -1 or oxide is a -2. Now we're looking at a group of atoms. So that's what really changes here. So if we take a look here at what's happening, if we have cobalt carbonate, we've got cobalt carbonate. That carbonate has a 2- charge. Since there's only one cobalt, that cobalt here has to be a 2+. So remember, CO3 has that 2- charge. That means our cobalt has the +2. So cobalt 2 carbonate. This next one here, we've got chromium nitrate. Now we got to figure out the charge of that chromium. So chromium, NO3 with 3 of them. Each one is a -1 charge. So -1 times 3 gives us a 3- charge. We've only got one chromium, so that chromium has to be a +3 charge. So that's where we get that chromium 3 nitrate here. This next one is a little complicated. So we've got copper and then phosphate, PO4, and we've got 2 of those. Each phosphate, PO4s, are 3-. So 3- times 2 gives us 6-. We need a 6+. 6+ divided by 3 gives me a 2+. So that's where we're going to get that copper 2 phosphate. And then lastly, titanium sulfate. So we've got our titanium. We've got 2 sulfates. Each sulfate is a 2-. So 2- times 2 gives me a 4-. We only have one titanium, so that has to be the 4+, which gives us an IV ending. Now, please take a look there. Carbonate, nitrate, phosphate, sulfate, okay? It doesn't matter how many we have. We had 1 carbonate, we had 3 nitrates, 2 phosphates, 2 sulfates. You don't change those wordings based on how many you have, okay? So, let's practice naming the following compounds. Now, these involve, again, both the simple ones where we don't need Roman numerals, and there are some that will need Roman numerals. Again, remember, you do not need Roman numerals if you are the first 2 columns, or if you are aluminum, zinc, or silver. So kind of that little diagonal staircase there. All right, so this first one here is in the first column, so we don't need anything special. We've got sodium, and then this ending here is called carbonate. The next one here, iron is a transition metal, so we can write down iron. Now we got to figure out the charge. We've got FeOH3. Each OH is a 1- charge, so we've got a -3 charge overall. That iron here has to be the +3 charge because there's only one of them. So we get iron 3, and that OH group is called hydroxide. Now this next one, we've got copper and sulfate. So I know we have copper. Copper is in the transition metal area, so we're going to have to figure out the charge. Well, the sulfate group, SO4, even though there's no parentheses around it, remember, because if we just need one, we don't need parentheses. But since they're that sulfate group, I'm just going to put a bracket underneath, is 2 minus, and there's only one copper. That means it has to be a 2 plus. So we've got copper 2 sulfate. Now the next one is aluminum. That does not need a Roman numeral. So we've got aluminum, and then that group here is called nitrate. The next one, we've got lead. Lead is not, I'll make that an A. Lead is not part of the first two columns or those three, so we're going to have to figure out a charge. So we've got Pb3, and then this is phosphate. We've got two of those. Each phosphate is a -3, so a -6 charge overall. That means we need a +6 charge over here. There's 3 leads, so 6 divided by 3 gives me a +2 charge, which gives me lead 2 phosphate. And then this last one, ammonium just gets its name. And then that S all by itself just gets sulfide, just like its old rule that we just talked about. All right, so that was how to name ionic formulas. Hopefully you started to kind of catch on to some of those rules so that naming the formula writing is a little bit easier. But let's go through some of those rules. So when we write ionic formulas, so anytime you are seeing a metal or a polyatomic that is really not with hydrogen, okay? So any polyatomic with like a metal or ammonium, or anytime really you're seeing a metal or a polyatomic for the most part without hydrogen, you are going to have to make sure that those charges between the cations and the anions match. Now, what do I mean by that? Well, you can't have a +3 charge and just a -1. That doesn't get us to 0. We're always trying to get to a charge of 0. So if we wanted to bond aluminum and nitrate, we know that aluminum has a +3 charge and our nitrate has a -1 charge. So because of that, we're going to need 3 aluminums and 1 nitrate. And so to write that out, we're going to just write aluminum and then we put parentheses around for 3 nitrates. Here's some more examples. Zinc chloride. Zinc has a +2 charge. Chloride has a -1 charge, so we're going to need 2 chlorides. Calcium carbonate. We have 1 calcium with a +2 charge. The carbonate has a -2 charge. So we just need 1 of each. Those balance out perfectly. And then lastly, aluminum sulfate. We've got aluminum that has a +3 charge. Sulfate has a -2 charge. The common charge there is 6. When I say common charge, you're thinking kind of like common denominator. So what's the common number between 3 and 2 that'll get you there? That common number is 6. So to get to 6, we need 2 aluminums, because aluminum has a 3+, so 2 times 3 gives us 6. And then we need 3 sulfates. 3 times 2 gives us 6. All right. Now, I'm going to teach you kind of a shortcut sheet. This is called the crisscross method. I don't love it, but it does work as long as you know how to use it. So let's say we had zinc chloride. Zinc has a +2 charge. Chloride has a -1 charge. We're going to cross those charges down. So initially, you're going to get zinc 1, chloride 2. And so we're going to not write that zinc or that 1 after the zinc. So you're going to get zinc chloride with that 2 after it. Now, calcium carbonate. This is one where if you don't know how to use this, you're going to get it wrong. So you might initially cross those 2's down, and you might initially get calcium 2, carbonate 2. But you need to reduce those. We can't have 2 and 2, so those need to come back down to 1. And when we have that, we have calcium carbonate like this. Sorry, there's not supposed to be so much of a space there, calcium carbonate like that. And then this last one does work pretty well. So we've got aluminum 3+, sulfate 2 minus. We cross those down. We get a 2 and we get a 3. So aluminum, 3, and then that sulfate, 2, my bad, 2 there. And sulfate's going to get a 3 there. Okay, so you just need to know that you're always looking to reduce. You don't write ones, that sort of thing. It does work for the most part. I just like to think more about charges. So use whatever works for you. All right, so remember that those Roman numerals in the parentheses tell us the positive charge on that metal. So if I say that we have iron 2 phosphate, that 2 in the Roman numerals tells us that I have a positive 2 on that iron. So iron, positive 2, phosphate has a minus 3. The common charge here is 6. So you're going to need 3 irons and 2 phosphorus. So it's iron 3. Oop, there's not supposed to be a comma there. I apologize. So iron 3 and then 2 phosphates. Again, the crisscross method does work here. So iron 2 and then phosphorus 3. So we bring those down a 2 and 3 and a 2. So we have iron with that 3 and then the phosphate with 2. Okay, so it does work. I just like to think more about the charges. And then the next one, copper 2 acetate. So we've got a positive 2 copper. The acetate has a minus. So we're going to need 2 of those acetates. So copper and then that 2 acetate. Again, copper 2 plus C2H3O2 with a minus 1. That 1 comes here. The 2 goes there. So copper with a 2. Okay, so again, that crisscross method does work. So let's take a chance to write some of those formulas down. You've got the names here. To pause it and work through the formulas. All right, so this first one, we've got silver nitrate. So silver has a positive charge, nitrate has a negative 1 charge. So we just need one of them. Our answer here would be silver nitrate, AgNO3. The next one, chromium, has a positive 3 charge from our parenthesis Roman numerals. Oxide has a minus 2 charge. So we're going to need 2 chromiums and 3 oxides. So Cr2O3. Barium phosphate. So we've got barium has a 2 plus charge. Phosphate has a minus 3 charge. Our common number here again is 6. So we're going to need 3 of those bariums and 2 of those phosphates. So barium 3, phosphate 2. The next one, aluminum chloride. Aluminum has a positive 3 charge. Our chloride has a minus 1 charge. So we're going to need 3 of those chlorides and 1 of those aluminums. So aluminum chloride like that. We've got nickel 3 sulfate. So nickel has the 3 plus charge. Our sulfate has a minus 2 charge always. So our common charge is 6 there. We're going to need 2 nickels and 3 sulfates. So nickel 2 and then sulfate 3. And then our last one, copper 1 selenide. So copper has a plus 1 charge in this case. Selenide has a minus 2 charge. And so we're going to need 2 coppers, 1 selenide. So it's going to look like this, copper 2 selenide. All right. Now we have what are called hydrates. And so most ionic compounds actually come to us from the factory as a hydrate. I shouldn't say most, but quite a few. And what that means is that you've got water embedded actually in the structure of the ionic compound. So you've got your positive and negative ions, but within that structure, you also have some waters embedded. And how we show that is those waters are going to show up after the ionic compound formula and a dot. So you're going to have the ionic formula, a dot, and then it's going to have some waters, and it could have a number in front of those waters. Oftentimes, it's not just one water. It's going to be more than one water. And so when we name hydrates, it's the exact same as our ionic compounds, except now we're going to add a prefix before the word hydrate. So copper sulfate, we named that just like we have this whole time. So we get that copper and the sulfate. Copper or sulfate is a minus 2. That means that this copper has to be a plus 2 because there's only one of them. So we get that copper 2 sulfate. And then we need to take a look at what's after this dot. After this dot, we have 5 waters. And so we're just going to write penta, and then the water, instead of saying penta water, we say pentahydrate. Okay? And then when we write hydrates, it's no different than anything we've done before. We first have to figure out the ionic compounds formula using charges, and then after that, you have to make sure that that's correct, but after that, you're going to write the number of hydrates after a dot. So in this case, nickel 2 chloride, we have nickel 2 plus and chloride 1 minus, so we need 2 chlorides and just 1 nickel, so NiCl2. And then it tells us hexahydrate. So hexahydrate is 6 waters. So this is the formula right there. All right, now we are going to practice writing the formulas or the names for these. So the top you're naming, and the bottom we're writing formulas. All right, so on the top, we've got calcium. Calcium does not need a Roman numeral, so we've got calcium chloride, and then we have 2 hydrates, so that is dihydrate. The next one, iron, is a transition metal, so we're going to need to figure out the charge of that. Iron, and then sulfate has a minus 2 charge, so that means iron has to have that plus 2 charge, so we have iron 2 sulfate, and then we've got 7 hydrates, so heptahydrate. The next one, sodium, is in the first column, so we've got sodium, and then we've got carbonate, and then we've got just 1 water, so that's monohydrate. And then our next ones here, these all happen to not need Roman numerals. So aluminum nitrate, so we've got aluminum here with a positive 3 charge, and nitrate NO3 has a minus 1 charge. So we're going to need 1 aluminum and 3 of those nitrates. So AlNO3, 3, then a dot, and then nonahydrate, which means 9 H2Os. The next one, barium hydroxide. Barium has a plus 2 charge. Our hydroxide has a minus 1 charge. So we're going to need 1 barium, 2 hydroxide, so BaOH2. And then octahydrate is 8 H2Os. Our next one, magnesium, has a positive 2 charge. Bromide has a minus 1 charge. So we're going to need 1 magnesium, 2 bromides, so MgBr2, and then a dot, and hexahydrate is 6 H2Os. All right, and the last type that we're going to have to name are compounds starting with an H. So a compound starting with an H, we could have 2 different types. We could have them not dissolved in water, which are going to be gases, or we could have things that are aqueous, which means dissolved in water, which are going to be our acids. So compounds that are starting with an H that are not aqueous, meaning they're a gas, these we're going to just simply state hydrogen without prefixes, so it doesn't matter if we have 2 hydrogens. We're just going to say hydrogen, and then we're going to say the other element ending in IDE. So hydrogen sulfide, hydrogen chloride, hydrogen bromide. And again, these are not aqueous. These would be gases. Compounds starting with H that are aqueous. When we say aqueous, we mean that they're dissolved in water. These are our acids. And so it would have to be stated that they're aqueous or that they're dissolved in water, or you would see this little parenthesis AQ. AQ stands for aqueous. And so there are 2 types of acids, each with their own naming scheme. So we have binary acids, which are just hydrogen and 1 other element. And then we've got what are called oxyacids, which contain hydrogen and a polyatomic ion. And that polyatomic ion has oxygen in it, so that's why it gets its name. So we're going to first start with binary acids. Binary acids are the simpler of the 2. These ones, we're always going to start with hydro, and then we're going to end with the element ending with IC. So it's not IDE anymore, it's going to be an IC. So we've got hydrochloric acid, hydroiodic acid. So that's how we that's how we name those ones. Now, if we want to write the formula from those acids, we have to first start realizing that hydro is telling us it's just hydrogen and one other element. And then the other thing that we need to keep in mind is that we need to keep those charges balanced. So hydrosulfuric acid, sulfuric tells us that we have sulfur, which is a 2- charge. And so we're going to need 2 of the hydrogens because each hydrogen has a positive 1 charge, so H2S. Now our oxyacids are a little bit more difficult. Our oxyacids, we're going to have to take a look at what kind of polyatomic ion we have and what its name is. So the first word is always going to start with the root of the polyatomic ion. So we could have sulf, nitrate, or we're not going to say nitrate, carbon. You're going to start with that, and then the ending of that root is going to depend on what the true ending is. Is it carbonate? Is it carbonite? Nitrate, nitrite, sulfate, sulfite. If it's sulfate in the formula, then we're going to end that name in an ic. So sulfuric acid would be H2SO4. And then SO3, that is hydrogen with a sulfite group. And so sulfite is going to turn into sulfurous acid. So there's a big difference there. The SO3 changes. You can see there that we have 1 less oxygen in the sulfite, SO3, compared to SO4. So the big thing there is that it's going to change the endings to those. So sulfuric versus sulfurous. If we see ic, it's that normal sulfate that we always know. If it's us, then it's 1 less oxygen. So SO4 goes to SO3. It still has the same charge of a 2-, but it just takes 1 less oxygen. Now, as far as naming that, formula writing goes, we are going to have to take a look at the root plus the ending. If it's an ic, then it's the 8. If it's us, it's the ite. So carbonic acid, we have carbon plus 8, so carbonate. We can figure out that 8 from the ic, so carbonic tells us we have the carbonate. Carbonate is CO3 with a 2- charge. Now, we are going to need 2 hydrogens for each carbonate. So H has a positive charge. Carbonate has a -2 charge, so we're going to need 2 of those and 1 of those, so H2CO3 for that. Nitrous acid. Now, I know that you don't know nitrate from our list. We know nitrate. So nitrate is equal to NO3 with a - charge. So if we are ending in us tells us it's an ite. So nitrite has 1 less oxygen than nitrate, so NO2. It's still got that -1 charge, so H plus with an NO2 - we've got a +1, a -1, so we can just write it HNO2. All right, so the last thing we need to practice are just naming these compounds. Some of them are aqueous, some of them are not. And then the last slide, we're going to go the other way, names into formulas. All right, so this first one, aqueous, so we have an acid. So we need to take a look here at what we're dealing with. That is the acetate. So we're going to shorten this, and we're going to say acetic acid. This next one is not aqueous, so we've got a gas. This, remember, if we're not a gas, we're going to start with hydrogen. And then we end with that IDE ending, so selenide. Okay, so hydrogen selenide. This next one, we've got, it's not an acid as well. Here we've got to start with hydrogen. And then we end with bromide. This next one is aqueous. We're dealing here, this is the phosphate group. And so phosphate turns into phosphoric. And then we end that with the word acid. This next one here is a gas. It's not aqueous, so this is hydrogen chloride. However, the next one is a little bit different. This one here is an acid. Remember that if we have an acid with just one other element, it's going to be hydrochloric, and then we end it with acid there. All right, and then the last slide, writing the formulas from the names. So if we take a look here, pause it, and then come back for the answers. All right, so we need to write the formulas for the following compounds. Hydrogen sulfide, since you don't see acid in it, it tells us we are just a gas. So hydrogen sulfide, we've got a +1 charge for our hydrogen. Sulfide has a -2, so we're going to need 2 hydrogens, H2S. Carbonous acid, this is a little bit different. Us tells us it is carbonite. And so carbonite is just a little bit different from carbonate. Carbonite is CO2 with a 2- charge, and so we've got our H+, our CO2 2-. That tells us we're going to need 2 hydrogens, so H2CO2 is our final formula there. Hydroiodic, this tells me I just need H and the other element. This other element, iodic, comes from iodine. Iodine has a -1 charge. The hydrogen has a +1, so HI is my formula. Hydrogen bromide. Sorry, both of these I should probably say are aqueous. My bad. Hydrogen bromide here is just a gas. Hydrogen and our bromine. -1, +1, so we just need 1 of each, HBr. Nitric acid, that nitric, so we know that we're dealing with kind of like a nitrate. IC stands for our 8 ending, so we're going to have our NO3- with our H+. Plus and minus, we're good there, HNO3, and that's aqueous. And then hydroselenic acid here, we're going to have H, and then our selenide is a 2-. So we need 2 hydrogens, 1 selenide, so H2SE, and this is aqueous because it's an acid. All right, and that finishes up our chapter 6.